Hello, hello. Welcome to another Fiddler puzzle. This week we have a circle, and on this circle there is a fuel station. And at that fuel station there is a car. And the problem is that this car wants to go all the way around the circle, but it only has a large enough tank to get exactly halfway around. And so if it went halfway, it'd be totally stranded out there and couldn't go any further. And so to correct for that, what we're going to allow it to do is we can have a fleet of cars that can try to refuel that car that wants to go around the circle. And so the way it's going to refuel is that a car can only have gas in its tank, but when it gets to another car, it can transfer gas from its tank to another car's tank. And they all have the exact same size tank. And so the original question is, how many cars will it take to get that first car all the way around the circle? And for this, I'm just going to show that it can't be done with two cars. And I'll kind of leave as a given that it can be done in three. But as we go into the extra credit, it will be clear that it can be done in three. So we'll think about this car. And I think the easiest way to think about this, why it can't be done with only two cars, is to think about the car's range and where it can go. So if I draw this half circle here, I mean, from the starting point, the car can get anywhere along that blue half circle before it runs out of gas. So the reason this is going to be relevant for thinking about why this can't be done in two cars, I'm going to shift this a bit until the car gets here. So let's suppose that the red car got here with a full tank of gas. Then the furthest it could get from here is all halfway around the circle again to the right side of the circle. And that's the far it get. That's as far as it could possibly get from this starting point with a full tank of gas. Now, what that means is at some point inside this blue circle, the car is going to have to get refueled, right? The car is going to have to get refueled. So now consider a green car trying to refuel the red car somewhere in the blue section of the circle. Well, the green car can get to the red car, but if it gives any of its gas, right? So for the green car to get to the red car, it's going to use half a tank. Now, if it gives any gas at all to that red car, even here, this is as close as it could possibly get to the fuel station on the blue circle. Then if the green car gives any of its gas to the red car, it will then have less than half a tank left, and it won't be able to get back to the fuel station. So there's no way to do this trip with only two cars, right? It won't be able to get back. So we need a third car. And so the answer to the first part of the question is just three cars. We can show that, well, that third car, I mean, not show exactly, but if you just want to think about the fact that a third car could refuel the green car a little bit, maybe halfway between the red car and the fuel station. And so that there is a way to get some extra bit of gas into the green car. So there is a way to do it with a third car. But we want to think about for the extra credit is, given that we can do it in three cars, how can we do it efficiently? So to think about what an efficient strategy here would look like, let's consider just some random distance d along the circle where the green car is going to head to the red car and refuel it and come back. Okay, so and to make this a little bit more concrete, instead of thinking about fueling this red car, I'm going to instead just think about what happens if I just I want to deliver some certain amount of gas to that point D. And we don't have to think about the fact that there's a red car there receiving the gas, but we're just going to say, I want to bring a lot of gas to this point. Right, so suppose I want to deliver not just a tank of gas, but 1,000 tanks of gas, that distance D. And the reason I want to do this is because I don't want to think about the kind of waste in the sense of I'm not using a full trip. And so I kind of have this waste built into the problem where I don't use a full trip. I'm going to ignore that for now. It's going to be important later, but for now, we're going to kind of assume it away. How much gas is it going to take to do that? Well, I'm going to measure my distance d in terms of tanks of gas rather than a distance like miles or something, just to keep all the units nice and comparable. So each trip that the green car takes is going to use up its entire tank of gas, right? Because I'm presuming here that when it gets to the point D, it's going to give as much gas as it possibly can before it goes back to refill. I think it's pretty obvious why that would be optimal. So I'm just going to assume that here. And so each trip that it takes to the point D is going to use a tank of gas, and it's going to deliver 1 minus 2D tanks of gas. Where does 1 minus 2D come from? Well, it takes D tanks of gas to get to the point, and it needs to save D tanks to get back. So for each trip it takes, it's wasting, in some sense, 2D tanks to get there and back. And the remainder, that 1 minus 2D, is what it can actually deliver. So the total gas I'm going to need is 1,000 divided by the number of trips. It's going to, divided by the amount of gas I can deliver per trip, right? So this is going to be the total number of trips that the car takes, the green car is going to take to deliver that gas, which is because the car takes one tank. That's how many tanks it's going to take. So now there is some rounding error here, right? So if D is some really strange number where 1 minus 2D is not a factor of 1,000, or I mean, it's not going to be a factor because it's not going to be an integer, but if it doesn't neatly divide into 1,000, then I'm going to have some rounding error. But assuming that we end up with a distance that works out nicely, this is kind of the best ratio we could possibly get in terms of how to deliver that gas. Now let's consider a different strategy where I'm still delivering to point D with a green car, but I have a second car, a yellow car, that I can also use. And so the way I'm going to think about this strategy is the yellow car is going to deliver gas to the green car at some point between the fuel station and D. And the green car is going to go back and forth to that point where yellow is delivering the gas and head it back. And now it turns out that you can think about this just as yellow is going to deliver a bunch of gas to some point between the fuel station and D, and green is going to shuttle that gas from there to D. And we don't have to think about the fact that there's actually a transfer because there's no time limit, right? So a way to think about that is whenever the yellow car needs to do a delivery, the green car will just wait at the meeting point until it's full, and then it will go to D and deliver the gas and come back. And then it will, yellow car can, if there's any excess gas in yellow car's tank during that process, the yellow car can just wait at the meeting point while the green car goes there and back. It takes whatever gas is left in the yellow car's tank, or as much as it can spare, before it goes back to the fuel station. And then at that point, it will fill up and do the trip again. And so that is the way it would actually work in practice. But you can abstract away from that and just think, well, yellow is going to deliver a bunch of gas to some point in the middle of between D and the fuel station, and green is going to take all that gas and deliver it to D. So again, I want to deliver 1,000 tanks, say, at distance D. And we're going to say that because I don't know where in the middle I'm going to choose a point yet, I'm going to divide that up into two other numbers where the green car is traveling some distance D1 and the yellow car is traveling some distance D2, where the sum of those distances is the entire distance they need to go. So D2 represents kind of the spot that they pick to meet in the middle, and D1 is the distance from that to the endpoint. So just like before, I'm going to need 1,000 because you can think of this as the green car is delivering gas from D2 to D, then and that distance is D1. The amount of gas I am going to kind of use to do that is 1,000 over 1 minus D, 1,000 over 1 minus 2D1. And so that's how many tanks of gas I'm going to need at D1 to accomplish this. Sorry, not at D1, at D2. Starting at D2, the meeting point. And then how do I get that many gallons to D1? Well, I take that number, 1,000 over 1 minus 2D1, and divide that by that same fraction, one, but now using D2 because that's the distance that the yellow car is traveling. And so that's how many tanks of gas I'm kind of starting with at the fuel station to get that much gas to D1. So how do I max? So because I have this, and again, I'm going to assume away any possibility that these numbers do not neatly divide into 1,000, and we end up with kind of some wasted distance where the car takes a trip, but didn't kind of use up its full tank, either in delivering gas or traveling. So we're going to ignore that away for the time being and just assume that that's right. And now what I want to do is I want to make this, I'm dividing by both 1 minus 2d1 and 1 minus 2d2. And I want to make that, it's actually the product of those two things because I'm dividing by the product of those. I want to make that as large as possible to make this total as small as possible. So how do I maximize that product? And again, I have this constraint that d1 and d2, the sum of them is the total distance I need to travel. Well, I can substitute in for d2 because I have that constraint. So d2 is just d minus d1, and then I could do the distribution of those terms, kind of sort a little bit. And if I take the first derivative here, then I end up with this, which simplifies a little bit. And if I set that equal to 0, then I'll end up with d1 is d over d is halfway, right? d1 is halfway, half the distance. And just as a side note, right, this 1 minus d times 1 minus d, and that's what I would get if I plug in d1 equals d2 equals half d into this up here. That's going to be more, if I do that, if I FOIL that out, it's 1 minus 2d plus d squared. And, d is at least 0. So d squared is positive. I mean, I guess d squared is positive anyway. This is going to be more than 1 minus 2d, which is what I would, the denominator of that fraction I would use if I were just using one car. So using two cars, assuming I'm, being efficient and I'm using full tanks of gas for every trip, then using two cars is always going to be more efficient than using one car. So that's an important side note to think about here. Well, let's go back to this circle now. And I want to think about some points on the circle. And I'm going to, instead of labeling them in terms of the distance, the fraction of the circle, I'm going to label them in terms of how much gas it takes to get there. So it's going to take 1/3 of a tank to get 1/6 of the way around the circle. It'll take half a tank to get 1/4 of the way around the circle, right? It'll take 2/3 of a tank to get 1/3 around the circle. It'll take a whole tank to get all the way around, right? And so on and so forth. So that's how I'm going to measure distance on this circle, is in terms of tanks of gas. So now, why do I think about these points in particular? Because I'm going to start thinking about what it's going to take in terms of actual gas cost to bring gas places, and noting that there may be some waste here where a car doesn't use an entire tank of gas, but still has to drive the entire distance to accomplish its goal. So let's say I want to get a tank of gas to 1/3 of the way around the circle. How can I do that? Well, I could do that with one car, and it's going to take 3 trips. Why 3 trips? Well, each trip to 1/3, it can deliver 1/3 of a tank of gas. I can plug it into the formula 1 minus 2/3, but to know that there's no wasted gas, I need to know that each time I get there, I'm delivering 1/3 of a tank. So if I do it in 3 trips, I'm exactly going to get 1 tank of gas to that 1/3 spot. And there will be no extra left over. So it's going to take 3 tanks total to do that. I want to use 2 cars instead of 1 car. Well, now the meeting point between the green and yellow cars is going to be 1/6, halfway to 1/3. And from there, I need 3 half tanks to get to that point in order to deliver 1 tank to 1/3, right? So if that distance is 1/6, 1 minus 2 times 1/6 is going to be 2/3. 1 divided by 2/3 is 3 halves. So that's where that 3 halves comes from. It's basically, the same formula, 1 over 1 minus 2d, but d is now 1/6 instead of 1/3. So I need 3 tanks to get to that halfway point, which means the green car is going to have to take 2 trips, right? So why 2 trips? Basically, you're going to have to take the ceiling of whatever this is. That's how many trips it's going to take. So it's going to take 2 trips, and plus it has to get to 1/6 and back to fuel. And so if it takes 2 trips between 1/6 and a third, that's 2/3. Plus it takes a trip from the fuel station to a sixth and back. That's another third. So driving a total distance of one, plus whatever fuel delivery it's doing. And so to get 3 half tanks there, I just square that to get the number of tanks I need from the start. That's going to take 3 trips for the yellow car, right? Because again, you take the ceiling of 9/4, that's 3. So it's taking 3 trips to a sixth and back. That's 3 times 2, because it's going there and back, times a sixth is 1. So it's also going 1 tank in distance. So the total distance driven by the green and yellow cars is 2. And so there's 2 tanks of gas used in driving, and there's a tank of delivery. So it's taking 3 total gallons. So, here we've already gotten to the point where using 1 car, using 2 cars to refuel is equivalent, right? There's no benefit to getting that second car here. And if I want to think about, and just as a side note, right? I guess it's not a side note. This is the point: is that 3 tanks is quite a bit more than if I just use a simple formula. A tank of gas divided by 1 minus 2d squared, right, which would give us 9/4, right? There's quite a bit of difference between those, which represents the fact that the green car delivering gas to a third and the yellow car delivering gas to the green car. In both cases, you end up with some waste where the cars make the full trip but don't deliver the full amount of gas. And so your ratio ends up being a bit worse. So we lose quite a bit by being inefficient there. And so now I'm going to think about, what if I only want to bring a third of a gallon of gas to 1/3? And now, why is that something relevant in particular? It's because if I wanted to refuel the main car at a third, well, the red car will only have used a third of a gallon of gas at that point. So I only need a third of not a gallon, a third of a tank of gas. That's how much gas I'll need to deliver if I want to do that. So if I want to do this with 1 car, it's only going to take 1 trip, right? And there's no wasted gas. It takes a third of a tank to get there. It can deliver that third tank of gas and go back, and there's no waste whatsoever. And it's going to use 1 tank total. And if I want to use 2 cars, well, using the same exact ratio as before, from a 6, I need a half tank of gas. And the green car is going to take 1 trip, because that's the ceiling of 1/2, for a total distance of 2/3, right? Because it's going to go basically to 1/3 and back. You can think of that as going from 1/6 to 1/3 and back, and then separately from the fuel to 1/6 and back. But since it's only 1 time, you can just think of it as going there and back. So I need 3/4 tanks from the start, which means the yellow car trip is also going to take a trip, and it's going to go to 1/6 and back for a total distance of a third. And so the total gas used is 4/3, right? One in, I'm calling this waste, but it's really it's not waste in the sense of they are doing this inefficiently. It's waste in the sense of they need to drive the fuel around, right? So it's 1 in driving gas for the yellow and green cars, and then there's that 1/3 delivered. So actually, two cars takes more gas to deliver than 1 car if I only want to bring a third of a gallon to a third. So I want to think back to this circle and why these points are important. Like, why did I choose these points to label here? And it wasn't random. It's because these are the points where you can do things somewhat efficiently, right? So 1/3 is a point where I can deliver efficiently. It's kind of the furthest point I can deliver efficiently. Actually, no, sorry. It's the only point I can deliver efficiently with 1 car, right? So by efficiently, I essentially mean it goes there, it delivers, and it comes back. And it does so with kind of minimal waste. I guess I could put 1/4 as another point that's somewhat efficient, because there it does the same thing. We'll see why I use 2/3 in a second, but basically 1/3 is going to be an important point for thinking about the strategy. A half is an important point because that's where I can really efficiently deliver with 2 cars, right? So both cars are going to meet at a quarter, which could be somewhat efficiently delivered in one car. Now, the reason that a fourth is not really relevant is um, it's not really efficient to deliver gas to the red car at one fourth, because if the red car, when it's at a fourth, can only take a quarter gallon of gas, and so if I'm only delivering a quarter gallon of gas to a quarter, then I'm going to use three quarters of a tank to deliver a quarter gallon of gas. That's not, I mean, it's a ratio of 3 to 1, so it's still efficient in the same way that one third is. Um, but it's not using a full tank of gas to do it. Whereas one third has the same ratio, right? One to three. And really, any point where I deliver gas to the main car between 0 and a third is going to have that 3 to 1 ratio. But one third is kind of the maximum distance you can go before that runs out and you start need using two cars. At a half, we can efficiently deliver two cars. 2/3 is a point. It's double this one third distance. So if one third is kind of an efficient um, spot for one car, then 2/3 seems, at least intuitively to me, to be an efficient spot for two cars to deliver. And it turns out that is true. You can deliver there with no wasted gas, and that works out quite nicely. So anyway, um, those are some efficient points. And now I'm going to switch to an animation that hopefully can help us. So here I have an animation from my friend Lal. Because I didn't do it, the colors are a bit different than how I explained it before. But the red car here is still going to be the main car, and it's going to be refueled by the blue and yellow cars. And it's going to go counterclockwise around the circle instead of clockwise, but hopefully that won't be too confusing. So we can see that the red car is our main car. It is continuing up, and they both go to a third, and at a third, the blue car gives that third of a gallon to the red car. And now that's important because at that point, the red car was totally full on gas, right? It got to a third, so it used a third of a gallon, and it filled the tank up, and then the blue car comes back. And so end fills, here's how much gas has been used essentially. So at the start, all three cars were full of gas. And when the blue car gets back, this end fill is going to go up to 4. And then at one third, we're going to essentially ignore this red car and let it go halfway around the circle. And so now the yellow and blue cars are going to go to head back because they need to get to 2/3 to refill the circle. Now what happens at one third over here is that the yellow car refills the blue car. Right, so the blue car is like our green car in the example, and the yellow car fills the blue car here so that it can get to 2/3 somewhat efficiently. It's going to go back and refill, and the blue car and the red car are going to meet up here at 2/3, or I guess 4/3 from the total clockwise perspective. So they're going to keep going. The blue car will meet the red car. The yellow car will get another tank of gas because it's going to have to refill blue again. It's going to refill them both actually, right? So it's going to go there. It's going to refuel the red car, bring it back, get some gas, and then it's going to go refuel the blue car and bring it back. And that whole thing took 6 tanks of gas, right? And they will both get there. And now here I can drag the cars manually a little bit and show you two kind of equivalent strategies. So in the strategy you just saw the animation for, right? The red car got refilled by the blue car at a third, right? And so the red car was now full. The blue car went back, and then the red car continued on. And in the strategy you saw, the red car went all the way over to 4/3 before getting refilled again. But it could equivalently happen that the red car goes to 2/3 and gets filled again. Now, going from 1/3 to 2/3, the car is going to use a third of a tank of gas. And now in this case, I'm actually not going to want the blue car to go back right away. So the blue car has a third of a tank of gas when it gets here. It took a third to get here, and it gave a third of a tank to the red car. So from here, the yellow car could go give a third of a tank to the blue car and come back, right? It could refill back up and do the exact same thing again. And after it's done that, now the blue car is full of gas. Now at this point, note that the yellow car has gone there and back twice. So we've had 5 times. So the red car has a tank of gas, the blue car has a tank of gas, and the yellow car has a tank of gas, and the yellow car is refilled twice. So we're kind of at 5 total tanks already, but the all the cars are still full. Now at this point, the blue car can go to the red car and back, right, filling up the red car because the red car had sorry, I said it was full, but that was incorrect. The red car had 2/3 of a tank, and the blue car goes a third, refills it a third, and comes back. Now the blue car is empty, but the red car is full. And since the blue car is empty, we've got to go back here, and the yellow car can now give a third of a tank to blue, which is enough to get it home. And now they both come back. And now at this point, I want to be careful, right? I'm only going to refill the yellow car. And now we've had 6 fills when we get here. Now from 2/3, the red car can use half a tank to get to 5/3, right? And then from here, the yellow car can do one more trip with its full tank of gas and bring the red car home and not refill. And that will use 6 total tanks of gas. So that's an exactly equivalent strategy. The only difference is instead of refilling the car up here at 4/3, we're doing a smaller refill over here at 2/3, but it's kind of exactly symmetric, right? If you think about the red car gets a third of a tank here and a third of a tank here, that's exactly symmetric to it getting a third of a tank here and a third of a tank here, right? And in both cases, it's getting filled 3 times, right? It could get a third of a tank here, a third of a tank here, right? And then a third of a tank here. That's one way of doing it. Or it could do a third of a tank here, get ignored until it gets to 4/3, a third of a tank here and a third of a tank here. That's exactly symmetric. But we can actually do a little bit better than that. So rather than refueling the red car at, roughly 1/3 and 2/3 and 5/3, we could instead refuel the car basically at 1/2 and 3/2, and that will end up being a little bit better. So here's how that might look. And there are a couple ways that you can vary this and not effectively change the outcome. So here's one way that you might do it. So both cars or all 3 cars might head up at the same time, and then right as you're about to get to a quarter, the yellow car is basically going to fill up the red and blue cars over here, so they're both full. So in other words, essentially, if all 3 cars are getting to 1/4, then they've used in total 3/4 of a gallon of gas. So yellow can fill them both up and then head back to the fuel station with its quarter tank, and the red and blue will both be full. So then they'll continue on until about half. When they get to the halfway point, now yellow is going to fill up. The red is going to get filled up by the blue car. And now the blue car will be at half tank. So why are they going to be at half a tank? Well, they started out both full at a quarter. So when they go another quarter, a half tank will be gone. And so when blue fills up blue will still have half a tank, which is just enough to get home. And red can keep going around. Now, they can keep going around. Blue will head back to the start. And now we can have blue and yellow both head over here. Now, when they get to a quarter, what's going to happen is blue is again going to fill up yellow. Yellow is going to fill up blue here. And then blue and red are going to head towards each other. So red is still going. Since they were full at 1/2, they're going to be empty at 3/2 over here. So blue and red will meet at 3/2. So try to think, well, how much gas will they have left when blue gets to red? Well, red's going to be out, right? How much will blue have? They'll have 3/4. So try to think about how much gas maybe. I guess it doesn't actually matter how much it gives, as long as it's more than a quarter of a tank. But they can get some gas to red. In this case, blue gave red a quarter tank, just enough to get to yellow. And blue was left with half a tank. Then as they come back, red's going to run out, blue's going to still have a quarter, but no matter how the gas is divided up, as long as there's enough for both cars to get back here, we're going to end up with 3/4 of a tank of gas left between the 3 cars, which is going to be just enough for the 3 cars to squeak back into home. And you can see that we ended up filling the gas 5 times. And so just to show you, why it's at 5 times, well, to start, right, all 3 gas tanks are full, so that's 3 fills right there. They're all going to head out. Yellow's going to come back and fill right here. Blue's going to come back and fill as well. They're all going to head back, and they don't have to fill again before they get back. So that's 5 tanks of gas that gets used in this strategy. And I feel pretty good about that 5 tank number. I have kind of pseudo proof, which leads me to believe that there's no way to do it in less than 5 gallons. So even though in theory from the formula that there might be some ways, because I'm not being so precise about how to deal with the waste that comes from a car not using a full tank of gas. I still think 5 is the least you can do. So here's my pseudo proof. So the red car is going to have to get refilled at least twice, right? It's going to have to get refilled on the left side of the circle and the right side of the circle. If I had a fourth car, in theory, it could be refilled only once at the very end, but we're going to ignore that because we only have 3 cars to work with. So the green car is going to refuel the red car over here on the left side of the circle and on the right side of the circle somewhere. I don't know where, but it's going to happen in those 2 spots. And the distance that the green car travels then is going to depend on how far the red car traveled. But the red car can travel at most half the circle because that's as far as a tank of gas can go between refuelings. Which means that the green car, right? So the green car has to go the entire rest of the circle that the red car didn't travel, which is half the circle as well. And what that means is since the green car is going there and back, that is the green car traveling essentially the entire circle, and the red car also travels the entire circle. So that is 1/4 of a tank. Sorry, that is 4 tanks of gas just with the red and green cars, ignoring the fact that the green car is going to have to get refilled um, on at least one of these sides. Now, how much gas could that possibly take? Well, you know, you could say that, well, the green car might only get refueled on one side. But if the green car only gets refueled on one side, that means on the left side, the red car has to get refueled at 1/3 or earlier to be optimal, which means that we're, in a best case scenario, we're at that 1/3, 2/3 strategy, which is using 6 tanks of gas. So if we're going to do better, we're going to have to refuel the green car on both sides. But now if the green car is getting refueled by the yellow car on both sides, what that means is the yellow car is traveling half the distance that the green car travels, by the exact same logic is here, just on one side, which means that the yellow car is traveling at least half a circle because it's traveling half the distance that the green car travels if the yellow car only makes one trip per fill, which the best you could possibly do. So in that case, the yellow car is traveling one full circle, which adds another tank of gas. Not a full circle, sorry. It's using a full tank of gas. It's traveling half a circle, which is a full tank of gas. And so that gets us to 5 tanks of gas. So I'm pretty sure that is somewhat of a proof that you can't do better than 5 tanks of gas. So anyway, that is my solution. Hope you learned something, and I will see you next week. Bye.